Good evening to one and all present here. My name is Dhyan, and I'd like to extend a warm welcome to Dr. M. Selvakumar, along with everyone who's attending the event today. He will be delivering a talk on polymer blends, composites, and applications. I'd like to talk a bit about the initiative Cognizance. We have arranged for a week of interdisciplinary talks in different fields. And the main motive of this event is to bring everyone interested in research or interested in actually learning something or working on researching something. So it's great that everyone's attending, and the participation yesterday was amazing. We hope to see it maintained throughout. Uh, Before the presentation begins, I'd like to define the structure of the talk today. Our speaker will be giving a presentation on the topic, and it will be followed by a question and answer session. So if anyone has any questions during the presentation at all, you are free to put them down on the chat. The chats are open for discussion as well. So any debatable points, anything anyone finds interesting at all can be discussed over there. uh, your for all the attendees, your video cameras and mics will be switched off, and yeah, our team will also be moderating the chats. So it's a request from our end to keep the chats very focused or based on the technical aspect of the talk. Uh, Having said that, I would like our moderator, who is Devangshi Debraj, to introduce the speaker for today.
Good evening, everyone. Am I audible? Good evening and welcome to the second talk of Cognizance. I am pleased to introduce the speaker for the evening, Dr. M. Selvakumar. An assistant professor at our very own Manipal University, Dr. Selvakumar received a PhD in chemistry at NITK. He has been the principal investigator for multiple large-scale research projects, including one for DRDO, and was also a junior research fellow at the Central Electrochemical Research Institute, CSIR. A well-established researcher, he has contributed to over 60 research articles with more than 1,300 citations. His topics of interest include polymer blends, composites and electrolytes, electrochemical power sources, and supercapacitors. Today, we have the opportunity to learn about his research experience with polymer blends and composites and their applications. Sir, the floor is yours.
Yeah, thanks for your nice introductions. So I'll share my slides. I hope the slide it might be visible to all. So today I'm going to talk about the polymer blends, composites and their applications. So the content of the talk is the first 15 minutes I am going to discuss molecular interactions between the polymer and solvent. Then next 15 minutes I am going to discuss polymer blend miscibility in the solvent and its applications. So that is the first half an hour program. The next half an hour program is introductions about the polymer composites and its applications, and what are the research I am doing in the MIT that I am going to discuss. Okay. So let us first the outline of the work is preparing a polymer solution is slightly difficult from the ordinary low molecular weight solutions. Say for example, you can take a sodium chloride and put it in a water, right? Easily it will get dissolved. You can take a polyvinyl alcohol and put it in a water, it won't going to get dissolved at all. So that means the mixing of a polymer solutions in a particular whether it has taken place or not, first we have to discuss. So whether there will be a proper interactions between the polymer and the solvent molecule, it's there or not, we have to find out. Thereafter only it's possible to go and check the polymer blend miscibilities. So blend means it will comes in a two polymer in a common solvent, right? to identify, to first go to the blend miscibility, first you have to come and discuss come and identify whether there will be any molecular interactions between the polymer and the solvent. So that's what the first 10 minutes I would like to discuss molecular interactions between the polymer and the solvent. Thereafter only I would like to go for polymer blend and miscibilities. So first we have to prepare the polymer solutions, right? Once you prepare the polymer solutions, of course, it's a chemical engineering point of view we have to discuss, right? As a process engineer, right, you have to monitor your process. Say for example, you can take any kind of reaction, say plus B reactant. So how much amount of the reactant you are going to feed in the reactor, and how much amount of the product it might be comes out of the reactor, then how much time it has taken place in the refluxer, finally it will go to the storage tank. That everything as a process chemical engineering you have to monitor. So here to say normally what we have to monitor, that means we have to find out what is the viscosity of the solutions. It might be a low molecular weight solutions, or it might be high molecular weight polymer solutions, whatever it may be. So viscosity, once it's related, thereafter next you have to find out what is the density of the solutions. Then only you can came to know that. So if it's a reactor is there, how much amount of the reactant I can feed into the reactor, that you can using the calculations you can find out. The same concept only I have followed here. That same concept I have taken, and I try to identify whether there will be any interactions between the polymer solutions and solvent. If there is any interactions, then we can go for doing the blend miscibilities. If there is no interaction between your polymer and solvent, there itself we can drop it. No need to go for any blends, right? Once if you prepare the polymer blends only, it's possible to go for any applications. So we are in the first preliminary steps. First, we are preparing the polymer solutions, a series of solution, 1% solutions we are preparing, or 2%. From that, you can make a dilute, right? If you have the higher concentrations, you can come to the lower concentrations very easily. So 2% to 1.8, 1.2, 1.6. Like that you can prepare and find the physical properties of the polymer solutions. What are the things I am going to find means density, viscosity, ultrasonic velocity, and a refractive index. Right? Using that, I am going to do some physical chemistry calculations. Of course, it's a interesting point of view, chemical engineering aspect. I am going to do some calculations. From that I can try to identify whether there is an interaction is there or not. Okay, so these are the parameters. Of course, you know that what you mean by the viscosity, what you mean by the density, and the refractive index. Of course, you may not know that ultrasonic velocity, what it is, right? At a particular frequency in a solutions, you are going to create sound at resonance. See, some sound might be audible, some sound may not be audible. So we are going to fix a particular frequency, and we are going to create some vibrations in the solutions. Using that vibrations, what is the velocity of the solutions we are going to monitor. If you just Google it, you can came to know that what you mean by ultrasonic interferometer. Using that, I am going to calculate my calculations, adiabatic compressibilities and ultrasonic velocities and other things. Why I want to calculate, right? Without this, whether I can't able to just, I can mix polymer, and if the polymer is dissolved in a particular solvent, okay, solubility is there. Definitely there will be interaction is there. So why can't why can't I take that polymer and one more polymer I mix it in the same solvent? Why can't I go for preparing a blend? What is the reason behind that? Why I want to do that? Right? See, it's one of the proverb we use it that all the glitters are not gold. Like that, whatever you are dissolving a polymer in a particular solvent, it may not have a specific interactions. First, you have to identify what is there in interactions between the solvent and solute, right? So for that reasons we are doing, because imagine that sodium chloride in water or sugar in water, easily it will get dissolved, because easily it will get dissociated. We have taken n equal to 100 number of molecules, right? So it has to immerse in a particular solvent. The solvent should be induced in your coil chain. Thereafter, there should be dipole-dipole attractions or intramolecular hydrogen bonding has to be taken place. Then only proper migrations. So that means if you take a polymer and dissolve in a particular solvent, right? So change in free energy has to be takes place, either exothermic reactions or endothermic reactions. So enthalpy content has to change. So if there is an enthalpy content, right, either exothermic or endothermic, definitely change in entropy will come, because this process has to be taken place in the polymer molecules. Then only it's possible to monitor whether there will be interactions or not. Otherwise, we can't able to do that. So for that reasons, we are doing these calculations. Okay. So this is routine as a chemical engineering calculations. So I have taken the Gibbs-Helmholtz free energy equations. So yeah, that means this much amount of the solvent molecule I have taken 1% or 2%. I am going to dissolve in a particular solvent. Using that, some simple calculations. If you just go through the calculations, you can come to know that. If I am explaining more theoretical aspect, I can't able to come to application spot, right? So these are, you might be very familiar in the, as a chemical engineering point of view, you might be very familiar in that volume fractions and mole fractions and that calculations. So I may not interested to spend my time here. Okay. I want to know how I want to show that how I am calculating whether there is an interaction between the polymer and the solvent. Okay. You just see that this is a lattice parameter where the first I have taken the rho concentrations and I concentration, rho molecular weight, that means sodium chloride. So each and every lattice site, the solvent molecule it is there, so easily it will get and occupy. Whereas just see in the polymer solutions, it won't be. It's a gained molecules. So n equal to 100, like that it will be there. So then we can't able to came to conclusions whether there will be interactions is there or not. Okay, so using that, using viscosity, just now I'll come to the series of calculations, right? So this is n equal to mole fractions and volume fractions, then ultrasonic velocity, density, viscosity. These are just simply you can calculate, right? Now everything it's instrumented oriented, right? When I am doing, I used to do in upward viscometer from morning to night up to 2 o'clock in NITK. I measure all the parameters. But when I junior was joined, my guide procured the upward viscometer using point MR solutions. He just put it in the manual and he find out the viscosity. The entire work what I did 12 hours, he has completed within 3 hours using instrumentations. He has completed one paper within 10 to 15 days, but I have spent it for 6 months because using classical method I find out the velocity, density, viscosity, refractive index. Of course, we might be come to the chemistry lab, they might be explain you how to find the viscosity and density. Like that, this much amount of the series solutions I find out. So my aim is, so using that calculations, if that is psi 0, there will be a proper greater than 0.5 means that we can keep it constant. There will be no interactions between the component. That means what if you dissolve the polymer in a particular solvent, there will be no interactions. Then no need to go for any other applications. Either you have to change the solvent or either you have to change the polymers. So greater than 0.5 means some interactions it will be there. If there is a 0.5 means again marked degree of interaction is there. But if there is a less than 0.5, a strong interaction between your solvent and the solute. Here solute means here I have taken a polymer. So first I can came to conclusions what I have taken my particular solvent in a particular form polymer has some interactions. So I can go for further applications. Using these calculations, I can came to know that. You just see that everything it's considered less than 0.5, right? So then we can came to, so I have taken the PMMA and polymethyl methacrate. PMA means, PEG means polyethylene glycol in tetrahydrofuran. That also you got to check in a different temperature, because whenever you are going to applications, your product has to be work in a different temperature. So for that reasons we have check in a different temperature. So this is the first part we are doing in the blend miscibilities. Before going to that, so and PVC and CAB and PMMA CAB, polyvinyl acetate and CAB. PVC means polyvinyl chloride, CAB means cellulose acetate butyrate. Now, our aim is we want to discuss the polymer blend miscibilities, right? So for that, first conclusions we can came, what we have taken a polymer in a particular solvent, there will be a strong interaction is there. So the same solvent, I can take a two different polymers also to prepare the polymer blends. The interactions, it won't going to affect so much. So we may get a proper interaction, because when you may get a polymer blends properly means, so first I'll conclude the first part, that is solvent and solute interactions. So polymer and solvent interaction parameters, using a Gibbs free energy calculations we have did, and we can identify there is a proper interactions between the solvent and the solute. That part is over. Now we are coming to the, so this everything I have published in Indian Journal of Applied Physics in 2008 itself. Okay, next I am coming to the next category. Of course, today the highlight of the talk is polymer blends and its applications. Okay, miscibility of a synthetic polymer and biodegradable polymer in polymer in a particular solvent. Why you want to prepare the polymer blends? What is the reason behind that, right? So you want to say, for example, if you take a one polymer in a particular solvent, thereafter if you prepare any seeds, it might be give the properties of one polymer. Instead of that, if you take a two different polymer and in a common solvent, if you dissolve it and prepare the polymer solutions, it might have a give a two different property of a polymer. For that reasons, we got to prepare the polymer blends. Okay, first we identify there will be a proper interactions or not. The next one, when there is a miscibility, that you have to identify as a chemical engineering point of view, right? If there is a miscibility, say, right, I have to interact with students properly. Then only students will reason the class. That is called as a proper orientations, proper coordinations of the class. Like that, when the proper coordinations will comes, there will be a proper understanding. The same way, if you take a two polymer molecules and dissolve in a particular solvent, there should be, you should be get the proper miscibilities. Then only it's possible to prepare the polymer blends. Otherwise, we can't able to do that. If there is phase separations, is it possible to prepare the polymer blends? You can't, right? So you first you got to find out where the miscibility behavior is there or not. That you have to find out. So that we are going to find out now. So polymer blends, why you require the polymer blends? So sometimes we want a material that has some properties of one polymer and some properties of another. So instead of synthesizing a brand new polymers, we are going to mix the two polymers together to form a blend with all the qualities you want, right? But blend means it's a homogeneous solutions. So why when the US organizer is asked polymer blends, I told I'll talk on composites also. The reason behind that, if I talk up blends, easily I can go for composites. That's why I slightly extend the topic to the composites also. So composites means heterogeneous mixer. When it comes, that time I'll explain you. So we want to get the two properties of the polymers. So that you have to dissolve in a common solvent. Once it's dissolved, all the compositions, it won't give a miscibility. Say for example, 1% of PVC in THF tetrahydrofuran, 1% of cellulose acetate butyrate in tetrahydrofuran. So I got to vary my mixer 100%, 0%, 90% of synthetic polymer, 10% of biodegradable. 80% of synthetic polymer, 20% of biodegradable polymer. Like that, I have to vary my ratio. That means you might be get a 10 to 12 ratio. 10 ratio you might be get. Or the ratio it won't give a miscibilities, right? Or the ratio it never it shows the miscibilities. Maybe rare circumstance, some two polymers in a common solvent might give a miscibilities, but it won't happen at all. So you got to find out what is the ratio you are going to get the miscibilities of your polymer solutions. So that it's called as a one phase or a two phases means phase separations, because this region if you prepare your polymer blends it might have a good strength, and as well as what kind of applications you are thinking you can go for it. Already there is a phase separations between the two polymer, then we can't go for any other applications. So that we got to identify using chemical engineering calculations. Of course, nowadays it's a modern research, everything it's instrument based, right? It is not a classical methods. Once you prepare the polymer solutions, 10 different ratio you can using solution casting, right? Solution casting means you can take a petri dish and that ratio 90 to 10 or 80 to 20, that you can keep it in the petri dish. Tetrahydrofuran boiling point might be 70 to 80 degrees Celsius. So once you keep it in oven under 70 to 80 degrees Celsius, the solvent it might be evaporate and you may get a proper polymer film. That film you have to find out the DSC. DSC, from the DSC you may get the gas transition temperature. If you get a linear trend, right? So that it indicates the proper miscibility system. If there is, see like that, this region is showing a proper linear trend, whereas this region it doesn't show a proper linear trend. That means here weak interactions we can tell, and this we can tell the proper interactions. Of course, this is an instrumental method using FTIR also. FTIR, it's a, you can't find out proper stretching frequency. You got to go for DSC only, but DSC all the 10 film it's very difficult to take, because one DSC to run 700 rupees. So we for running 10 sample it's 7,000 rupees gone, means what we can't able to do as a student, right? So we got to do 9:1 means thereafter 6:4 and 3:7, like that. Three different ratio if you take also it's fine, because our aim is we got to find out where there is a proper miscibilities. Okay, that is the instrumentations method. Now again, this ratio of the polymer solutions you prepare, no, again you can find out all the viscosity, density, and as well as refractive index. Using that, these are the calculations. It's that is mu equal to del B N2, that is N2 means intrinsic viscosity. Intrinsic viscosity, relative viscosity, reduced viscosity, nothing else. If the x-intercept is touched when you are plotting viscosity versus present volume of concentration, that is called as a intrinsic viscosity. Reduced viscosity means intrinsic viscosity divided by the particular concentration is called reduced viscosity. I am not going to confuse that and all. My aim is I want to find out whether there is a proper interactions or not. So like that, some series of calculations. If I take an Excel sheet, it will go to A to Z column, then again A to another one more Z column. That means 52 columns I have to use. I am not interested to discuss that much, right? You can identify del B or a mu greater than 0. That means it's indicate the miscible. Less than 0, immiscible. And again, if you continue with some other parameter, alpha value is there. So alpha, if it is greater than 0 means that it acts as a miscible, less than 0 means immiscible. So series of calculations in a chemical engineering point of view, as an engineer, it might be do it very easily. If you develop one program, easily you can complete that. And again, using the flow reagents parameters, solubility parameters they might be given for each polymers. So we have taken two different polymers. That's why Ranta 1 and Ranta 2. So that polymer interactions or polymer solvent interactions, you can came to know that using this calculation. Then you can plot the graph. So reduced viscosity versus concentrations, NSP. So this value, if you extrapolate and it intercept y-axis, mean that is called as intrinsic viscosity. So that you can substitute, you might be able to get a mu and a alpha value. Just see that in the tabular column, some places we are getting a negative value, some places we are getting a positive value. That it indicates of clear miscibility of solutions when you are getting a positive values. If there is a negative values, there will be a no interactions. That's what it meaning. So that ratio you can skip it. Only you can prepare for 90:10 ratio of chitosanes and polyethylene glycol and 80:20 ratio of chitosanes and polyethylene glycol. No need to prepare for other ratio. We can only concentrate that to ratio and we can go for and prepare for any other applications. Okay, so this is because if you synthesize one molecules, what you will do? Normally you will go for the different spectroscopic. FTIR you will take, NMR you will take, a mass spectroscopy you will take. The same way in calculations we got to play with that. Chemical engineering calculations you got to do calculate the del B value, alpha value, mu value, everything should match with that. Then only it's a proper indications of the miscibilities. If after did all the calculations, again you have to verify with FTIR whether the 80 to 20 or 90 is to 1 proper stretching frequency you are getting or not. Right, here I have given A, B and C. So B and C you may get all the stretching frequency of chitosanes and polyethylene glycol. Imagine that we are just mixing two components. We are not doing any reactions here. So you got to get all the stretching frequency. If you are not getting any one of the stretching frequency, then there will be no miscibilities from the FTR point of view. Just see that here I have taken chitosanes and PEG in different temperature. I have did the DSC studies. First graph it's indicate 35 to 75 degrees Celsius, whereas second graph it's indicate 80 to 160 degrees Celsius. Why means the first one there will be a star peak we got it. The star peak it indicates there will be some immiscible state. So if there is a no salt peak where I am getting, because we have to go for different temperature. Salt peak also we can identify linear trend only, nothing wrong. So we did in the two different temperature and we can came to conclusions and our theoretical calculations it's exactly matching with the practical calculations. So then we can came to conclusions. The results are indicated blends are miscible in 90:10 and 80:20 in the entire temperature range. Of course, Journal of Applied Polymer Science, that paper I have published, and this what I shown the results I published in ePolymers. Okay. Okay. Now, okay, sir, I prepare the, I first find out as a, because we can't skip any theoretical, already theoretical framed by some good scientists. So we can't skip any of the scientists what they find out. So first we find out there will be a proper interactions between the molecular interactions between the polymer and the solvent, and we find out the miscibilities. So what kind of applications I can go for it? So polymer blends, no, it has a huge amount of applications is there, but I have did polymer blend electrolytes. Okay, so where I means you can use it for supercapacitor, you can use for batteries, even you can use for dye-sensitized solar cell. Of course, everything we are going to discuss. So what is supercapacitors, right? So supercapacitors is nothing compared to battery. It might have a able to develop the high power density. That means at a fraction of second, it may deliver very high power. Whereas battery, if you take, it might be give a constant energy density, whatever per kilogram, and constant power density. Whenever, wherever you would require very high power, particularly when you are starting your car, high power required. So that time you can hybrid with the supercapacitor. So the initial power backup it comes from the supercaps and the battery it will be safe. right? Like that, many places, even wherever you require the very high power, we can use it for supercapacitor. So this blend polymer, of course, there are two type of supercapacitor is there. One is carbon based supercapacitor, means that is called as a electrochemical double layer supercapacitor. One is material, electrode material, redox reaction based capacitor, means that is called as a pseudo capacitor. So in your electrode redox reactions will takes place, that is called as a pseudo capacitor. Electrode and electrolyte charge if it came and accumulate, based on that if we get an energy, mean that is called as a electrochemical double layer capacitor. So there are three different because all the either batteries, supercap, right, Dyson solar cell, whatever the material you require the electrolyte, there are again three different varieties there, but I have used for what we discussed the blend polymer electrolyte means. That blends I have converted to a blend polymer electrolyte. Now you may ask that, so electrolyte means we need a very good conductivity. Yes, of course. If there is no conductivity, we can't be able to fabricate our electrochemical power sources. So how I have to enhance the conductivity, that I have to work out. So what I did, so blend polymer electrolyte, one blend polymer electrolyte I have taken chitosan and polyethylene glycol. I have to dope with the inorganic salt because chitosan and polyethylene glycol both are non-conductive polymers. Right? It won't going to give any conductivity. So to improve our conductivity, what I am going to do, I am going to dope a lithium salt, lithium hexafluorophosphate, lithium perchlorate. Right here I have doped the lithium perchlorate. Thereafter, I have to check my conductivity of the blend polymer electrolyte. If it comes, right, you see that here also vary the ratio 90 to 10, 8 is like the 10 different ratio, and I have varied the lithium dopant salt means lithium perchlorate, and plasticizer if you add only again the conductivity it will be maintained, right? If there is no plasticizer, then we may not get a proper blend polymer electrolytes, and of course it will help also to enhance the conductivity. So all the ratio, which ratio it shows the maximum conductivity, that ratio of the polymer electrolyte I go to choose for to fabricating my devices. All the ratio again you can't able to fabricate, no use, because any one particular ratio it might shows a very good conductivity, right? So that, of course, why the conductivity? Because two polymer we have taken. Once you add a lithium salt, the conductivity is enhanced means you got to tell the scientific proof, right? Without scientific proof, if you tell anything else, your manuscript it won't accept, right? So I have explained the segmental motion mechanisms. So in the polymer chain, the lithium ion it will come and deposit and it will be transferred. So one chain to another chain like a Lewis acid and a Lewis base, right? So the jump of cation from one side to another side gradually changes the conformations of the polymer due to segmental motions. Due to that segmental motions of mechanisms, the conductivity of the blend polymer electrolyte as enhanced. Like that I proved that. Of course, you got to discuss. These are the research and discuss. We can't able to know that whether this mechanisms has taken place. But you have to justify your statement. This is the reasons, that's why the conductivity has to be enhanced. Otherwise, no use. And a reviewer may ask, what is the proof? How it has enhanced? This already segmental motion mechanisms, it's developed long back, right? That I bring to my proof of the concept. That's all. I didn't develop this segmental motion mechanism. I have taken that segmental motion mechanisms for this explanation. That's all. Right? So again you have to do in a different temperature. So whenever you are going to increase the temperature, the mobility of the ions is going to enhance. Due to that, the conductivity, the resistance of the sample, it might be going to decreases. So when in high temperature, you may get a very good conductivity. That is a proof of the concept. if you are not in, if you are increasing the temperature, the resistance also increase, then it won't going to behave as a good electrolyte, right? So when you are increasing the temperature, the mobility of the ions become higher, then we can able to identify, okay, it might be act as a good conductivity. So then dielectric constant is nothing but how the charge is stored in the electrolyte, that much only. Dielectric means storage of the charge. Using that, we can identify whether this polymer electrolyte is suitable to fabricate the devices or not. Of course, I fabricate the carbon-carbon supercapacitor. So if you get a carbon-carbon supercapacitor, you might be get a double layer response like this. And a charge discharge, next you have to do that. Charge discharge means you got to charge your device. So after certain time it will discharge. So how much you are charging? Say for example, it's a 1 centimeter squared electrode, 0.25 centimeter squared electrode. 2 milliampere if you charge, the 2 milliampere it has to be discharged. So how much time it has taken the 2 milliampere? Maybe 10 seconds, right? Another 10 seconds it has to charge. If it is happen, it is ideal capacitor. Normally it won't happen. 2 milliampere if it charge, 1.8 milliampere only discharge. So 10 seconds if you charge means only 8 to 7 seconds only charge. So 70% efficiency only we used to get. So this is a response of supercap and other calculations. Okay. And charge discharge, again you got to discuss one mechanisms. So when it's charging, charge it's go and accumulated anode and cathode. When it's discharging, the charge it might be comes out from the electrode and we may get the energy. So all the proof of the concept you got to explain in the manuscript. So this I have published in Electrochem Acta. Okay. So next conclusions. So here the idea behind that one I have taken a synthetic polymer and another one I have taken a biodegradable polymers. That polymer blend it acts as a good electrolyte. So after the device lifetime is over, you can easily degrade in the environment. Whatever the electrolyte also, because since it's a biodegradable polymer, easily it will get degrade in the environment. Okay. So next, of course, I would like to discuss the same work. Your Research Society co-president Achinanya did this work. Micro supercapacitor fabrications and its characterizations. He has taken same type of blend biopolymer electrolyte and he has synthesized a copper nanoparticle in our lab. PVP capped copper nanoparticles. So polyvinyl chlorine capped copper nanoparticles that we have confirmed with a SEM and XRD. So normally to prepare the nanoparticle, what you have to do, either very high concentrations, oxidizing reagent, reducing reagent, or high alkali when you are adding, it will get precipitate, right? So that precipitate time, the oxidation state of the copper, it might be changed. Due to that, we may get the nanoparticles and you have to add one stabilizers to stable the copper nanoparticles. So that procedure I have given. And of course, here that copper nanoparticles we mix it with the cellulose acetate propionate and as well as the graphite powder and diacetone alcohol and we prepare the ink conducting metal oxide ink we have prepared and we went for the screen printing methods, right? So this is a blend polymer electrolyte. Already we have discussed the corresponding morphology I kept. I am not interested to discuss this slide. I would like to show the exact essence of this work, right? What I did first, screen printing graphite I did, right? Not I didn't do, your co-president Achita and they only did entire work. So he has coated the graphite, right, and graphite layer. Over that he coated the screen printing of a copper nanoparticle that he have coated. Once you copper coated, you might be get a printed copper layer. Then exact that this one no, that we immerse in the blend polymer electrolyte, just we choked and taken. So once you choked and take, you might be get it like this. So this is anode and cathode just connected to the potential star. You might be get all the cyclic voltmeter, AC impedance resistance of the sample and charge discharge, everything we might be get. So this is a result, right? And this paper 2021 right? He came for just of course he did he only written the seed money project, right? He only I have given just overall presentations, overall idea only. He worked on within 1 month he got paper 3 point Q1 paper 3.2 impact factor, and of course one more paper humidity sensor he did, and another two papers we are working, and that paper it might goes to 6.2 impact factor. Very good data is there, but due to some routine work it's not going, but of course we try to push out some good journal. Okay, and next one is composites. Okay, up to now what I have talked on, everything I have talked on the electrolyte, I didn't go for the electrode material. So if you come to the composite, that all comes to the electrode material only. Composite means heterogeneous mixer, two dissimilar material you have to mix and you have to get a proper strength. So like that I have taken a polyethylene and polystyrene sheet. In between I kept a areca and banana fiber. So when I am keeping and I know that when the polyethylene polystyrene will melt. So that time using a melt casting I press, I will give a high pressure. So whatever this areca and banana fiber, no, it will go to polyethylene and polystyrene. Why we did this work means to whether the polyethylene and polystyrene whether it's degrading or not. But of course it doesn't degrade that. The reason behind that it's a hydrocarbon, there will be no further hydrolysis. That's why polyethylene and polystyrene it doesn't undergo degradations at all. That's why government banned for the polyethylene plastics. Okay. Okay, these are the things you might be studied in the composite. What is matrix phase? What is disperse phase? I'm not interested to discuss. Next, the same composites we did for the electrode material. What we did means, of course, you might be know one of the faculty, Soumya, she did the PhD under my guidance. That time this work we did. What we did, we have taken the multi-walled carbon nanotube and we have deposited the conducting polymer. So two different material that it acts as a composite and it acts as a good electrode material for batteries, supercapacitors. And in that multi-layer of the electrode, first we have taken one acids, polyaniline in a camphor sulfonic acid, and next one more acid and one more acid. Like that, supporting electrolyte you have to take nothing else. Take aniline and dissolve in a particular solvent, and thereafter if you apply the current or potential, the polyaniline will come and deposited over the carbon nanotube coated the electrodes. Like that we did for 3 to 4 layer. Why we are did a multi-layer means, because first layer it gives certain efficiency. Up to maximum layer we want to find what is the maximum current density it's giving. For that reasons we did a different layer. Okay, and of course again I have to confirm with the FTR spectra, and these are the tunneling electron microscope. Before that, this is a first SEM for the carbon nanotube and polyaniline and its composites B, carbon nanotube and polyaniline composite. C is only one acid, that is camphor sulfonic acid. D is a para-toluene sulfonic acid. E is the sulfuric acid. This is a multi-layer electrode. First layer, second layer, third layer over carbon nanotube. That we identify using scanning electron microscope and FTIR, and TEM also we did because a reviewer told you go to TEM and confirm that whether the carbon nanotube is there or not, because plenty of layer you coated. So what happened the carbon nanotube and whether three different layers are there or polyaniline is there or not, that you have to identify it out. So using that you see the TEM image of multi-walled carbon nanotube and polyaniline composites, and we identify where the polyaniline is there, where the multi-walled carbon nanotube is there. Right? This is nothing but selected area diffractions. Using that you can find out the particle size. And cyclic voltammetry, AC impedance spectroscopy, and charge discharge, and the corresponding characteristics. So this paper we have published in macromolecules, chemistry and physics. So that's all for the supercaps. And one more thing, composites, not only that work, we have derived different carbon, activator carbon from waste material, carbon fiber from waste material, and graphene we have synthesis. Then that graphene are mixed with the metal oxide and the metal sulfide. So this metal oxide and metal sulfide, it is a good hydrogen producers. Normally for the fuel cell we have to use the platinum. Platinum, the cost is very high. That's why fuel cell technology, it's not comes up. Now government is fully focused on lithium ion batteries. So I would like to give the lithium ion batteries what is the recent work is going. So this work what we did, we synthesis a different carbon and mix it with the transition metal oxide. Instead of platinum, we mixed it with the transition metal oxide and sulfide, and we find out at what potential we got a hydrogen evolutions. So this is activated carbon using PET bottle. Once I came to conclusions, polyethylene it won't degrade, so I come to the commercialization process. Using that bottle, I make a mess and convert it to a and then carbonize using a furnace, and it make a carbon powder. Thereafter you have to do a KOH activations at 800 degrees Celsius. The surface area got enhanced. We got it, of course, nearly activated carbon. We might be get a 2400 meter square gram, but our lab condition getting 900, it's too much. So that itself we got it, and we did then supercapacitor studies, activation proof, right? Then synthesis of the metal sulfate for the hydrogen productions. So this is using some precipitation method and hydrothermal method. We synthesis a carbon doped molybdenum sulfide. Okay, and that we have confirmed with the SEM and XRD. Thereafter we did a supercapacitor studies, and of course that already I discussed. I am not interested to come again. So then two different type of is symmetrical supercapacitor and hybrid capacitor. Hybrid means one side the carbon and one side the metal sulfate. Symmetrical means both side carbon or both side metal sulfate. Both are reactions we did and we given the relation. Now we go to tell here how the hydrogen evolutions reactions we did. So whenever if you go for in the cyclic voltagram, positive directions might be oxidation takes place, negative direction reductions it may take place. We want to find out at what potential our hydrogen evolutions might take place. For that you got to go for negative side and find out what is the potential to liberate the hydrogen. Of course directly you can't take activated carbon and the composites, because the reason is it won't liberate the physically activated carbon, no, it should be have a defect, then only hydrogen will liberate from the metal sulfide, metal oxide. So what we did, once we activated, again we deactivate the activated carbon. But of course it acts as a good support. Why we are adding carbon here means, for the metal sulfide and metal oxide, it acts as a good support. For that reasons we are adding. Okay. So once we deactivated, thereafter we did so this is a creations of the defect. You just see that this is a physically activated carbon and as well as a metal carbide. Here we create the defect. This defect will helpful to liberate the hydrogen from the metal oxide and metal sulfide. So that we did in the again cyclic voltammogram. When we are going the negative side, we can able to find out. Okay. So this is one kind of applications. Next, one more applications. I told you in Siri. Sir, why can't you use that brand polymer electrolyte for solar cell? The same thing we did, because photoanode, nothing else, titanium, any metal oxide synthesis will come as a metal photoanode. Photocathode is nothing but platinum based materials and metal polymer carbon you have to use. Again, for fabricating the dye-sensitized solar cell, you need a electrolyte. So the same electrolyte we have used, right? Blend polymer electrolyte. Not only that, and we have synthesis organic sensitizer, organic dye instead of platinum based dye, because platinum based dye is costly and we can't go for the commercialization purpose, because all the people should afford the dye sensitizer also. Otherwise, no one will go and buy that. So the cost of the material will be very high. So what we did, we have synthesis of dye molecules, right? So this is a simple precipitation technique. How you synthesis of copper, the same way titanium oxide. This metal free organic dye we have synthesis. for dye-sensitized solar cell fabrications. And of course, same electrolyte we have chosen, but instead of lithium doped, we have to use a Ka and iodine, because here for dye-sensitized solar cell fabrications, iodine it acts as a photon capture, right? And it is from the dye, it is helpful to regenerate the electron. So for that reason, in the blend, instead of lithium perchloride, we have to add a potassium iodide and a iodine. Okay, and we did the integrations now, because we know how to fabricate the same electrolyte. If you did a carbon-carbon, that acts as a supercapacitor. So titanium oxide with the dye and photoanode, and a platinum or a graphene, it acts as a photocathode, and polymer doped ionic liquid, what you have prepared the electrolyte, it acts as a in between these two. The same I2 plate, one side we fabricate the dye-sensitized solar cell, one side we fabricate a supercap. So that is called as a integration technology. So recently this work we have published in Journal of Solid State Electrochemistry. So I started 4:10. So another 10 minutes I will complete. The problem in dye-sensitized solar cell, the efficiency of the dye-sensitized solar cell, it might be 3 to 4%. Just you see this diagram, various solar cell efficiency values, right? It might comes the dye-sensitized solar cell means where it comes this, right? It might comes to 3 to 4%, very, very less. So we can't able to fabricate that much money after spending. The efficiency it comes very, very less. We can't able to do that. Maybe academic research might helpful. One student might complete the PhD, or one student may get a manuscript. But commercial, because in even your BTech project itself, if you come with the product, you are the CEO for your companies, right? You can commercialize your product. That's why I'm showing all the applications. Wherever you are interested, you can do that. So if you come out with in your BTech project one commercial product, after your BTech course, no need to go and a job for that. Directly you can create your company and you become a CEO and you can commercialize. That much opportunities are there. Okay, so then I thought that okay, we can't able to work out for the dye-sensitized solar cell. Then we shifted for the perovskite solar cell material. We have written one beautiful review article in Solar Energy, that is 2021. All the fabrications, what is the problem in the perovskite material, why we are doing perovskite material. Here the concept is slightly different. It's not a photoanode and photocathode. Here there will be no electrolyte. Instead of that, two layer will be there, that is ETL, whole transporting layer, electron transporting layer. In between you go to synthesis the perovskite, that you have to keep it, and there counter electrode will be there, HTL over counter electrode, FTO it acts as a photoanode and photocathode. Then why we are going means, the cost of perovskite it's very, very less, and the efficiency, you just see that this triangle it might be comes here nearly 24%. Still the silicon solar cell it's not commercialized. The reason behind that, it might becomes one rack. The battery, your UPS battery, it might be 10,000, but lithium that solar cell might be one rack, because after that on grid or off grid you require the batteries. So the cost it's very, very high. All the people can't be afford that, and the efficiency it's questionable. 48% we can't able to achieve even silica solar cell. So that's why now the trend is you have to do a tantalum solar cell. That is below one, you have to fabricate the perovskite. Above that, you can take another thin film, either silica or cadmium tellurium. If you did, the efficiency it comes to 48% tantalum solar cell. So that work we are doing with I am doing with now physics department. Of course, one more student is doing in perovskite solar cell. Okay. And one more interesting work, development of new organic and inorganic ink for flexible thermoelectric generator applications. What is flexible thermoelectrics? First, it's very simple. When the two temperatures, so right here material A is there, material B is there. So when there will be a temperature between A and B, or hot condition to cold conditions, voltage will be developed. So due to voltage generations, electron it might be going to create. That is called as a thermoelectric generator. Right? That means same concept, photoanode and photocathode, p-type junction, n-type junctions. So CPAC effect means that is called as a thermoelectric. Peltier effect means you are how the refrigerator and another things it's working. That means here you are going to supply the current and you will get a temperature, two different temperature. How your refrigerator is working, right? It's a very simple concept, right? Using that concept, some two students are working, and these are the calculations. I am not interested to discuss the calculations. And one good application, thermoelectric generator, these are the application. One good important, I'll come to this slide later, because why I am telling this field means, you just see that pacemaker, right? Normally in the pacemaker, now they are using the batteries. Now instead of battery, they are trying to use for thermoelectric generator because our body has a two different temperature. Using that, it helpful to pump the blood in the heart. So no need to battery because after some times if the pacemaker is not working, the patient might be died. Right? You can throw out your pacemaker, you can use a thermoelectric generator. So this work also we are doing. For that, these are the materials it's available. I'll come to the first slide. Yeah, this again conducting polymer and metal oxide and metal sulfate. But the only you have to synthesis, only the application is slightly vary. Right? Thermoelectric, everything it is available, all the experimental setup, everything we have and physics department we have, we can together work. Right? So this is the conditions required to enhance material choice of thermoelectric effects. Right? So electrical conductivity you got to get very high, Seebeck coefficients you got to get very high, whereas thermal conductivity you got to get a less. Then only you will get a good thermoelectric materials. So metals, insulator and semiconductors. Okay. You can select later, you can that PowerPoint, everything I given to your who is organizer, I am given to that, you can use it because the presentations for you. Then next one, draws of my presentations, lithium ion cell. Remember that how much money they are spending for lithium ion cell. Even our petrol price now it's 104 rupees. Even I can't able to afford continuously. Now instead of coming by car, I am coming by scooter. In fact, sometime I am coming by cycle itself. Right? So 104 and the government insisted go for lithium ion battery. So the simple technology where you are going to play with the lithium ion batteries, that I am going to give. I am opening plenty of research opportunities. Anode is nothing but made up of graphite. Lithium ion is integrated, nothing else. Separator polyolefin or polyolefin like a filter paper. Electrolyte, lithium hexafluorophosphate or lithium tetrafluorophorate. We have taken propylene carbonate and ethylene carbonate. So the your efficiency of the lithium ion cell, it is matter of how you are going to synthesize the cathode material. There are three type of cathode material is there. First one is olivine structure, that means lithium ion phosphate. Theoretical current density of lithium ion phosphate is 160 milliampere per gram. Whereas practically if you synthesis and did 130 milliampere per gram, the voltage it comes 3.2 volt, 2 voltage to 3.3 voltage. Since ion present in the lithium ion, the cost is very high, but the efficiency it's not so much. So we can go for only electric scooter because you need a very high power. Suppose if you take a car means at least some 400 to 500 kilometer you have to run. Either might be 100 kilometer again if you charge means no one go and buy a car. So might be this material, but you can see that now the trend we have achieved only 130 milliampere per gram. You can reach up to 160. Either the same method of synthesis only using hydrothermal synthesis. Second one is spinor structure. Spinor structure means lithium Mn2O4. The current density is 142 milliampere per gram for theoretically. Practically 120 milliampere per gram. The voltage is 4.5 voltage. But very high voltage, due to that the electrolyte might be decomposes and we can't able to continue further. right? And next one is the RAS, all the people are working lithium cobalt oxide, that is layer structure, right? So 282 milliampere per gram theoretically, practically we have achieved 220 milliampere per gram. Remember that the voltage also 3.8 and hold voltage, and here also due to high voltage it might be decomposes, and you can achieve only we can play with the layer structure of lithium oxide. So this is once you synthesis this kind of morphology, if you get your scanning electron microscopic or field emission scanning electron microscopic, you achieved some 50 to 60 percentage. And another one is at zero point 0.1 coulomb rate capacity, it will show 220 milliampere per gram. Whereas when you are charging 1 coulomb rate capacity, 160 milliampere per gram. Why we are checking 1 coulomb means, see, suppose if I go for charging my car, charging if it is take 10 hours, I won't go and prepare the car, right? Within 1 hour or half an hour it has to charge. Now we are going to petrol pump, maybe 3 to 5 minutes you may, or maximum 10 minutes you can fill your tank and comes out. Right there, when you are going for the very high rate capacity, that power should be retained, that if you achieve, you might have a product in your BTech project itself or in your MS or MTech or your PhD work. So that's why I have written, when battery is for charging rate, when battery is for charging, the rate will come less, because if you charge the car more than 10 hours, no one will going to buy. Okay. So these are my research students. So whatever I have discussed with you, I frequently discuss with my students. So the first, of course, you might be know the Soumya madam, and the first student completed and he is working as assistant professor in Christ University. And this students doing hydrogen evolutions under supercap, different carbon material and synthesizing, and as well as metal oxide and metal sulfate, and she is also going to submit the thesis. And next one is Ramakrishna sir, also you might be know that he is also faculty in printing department. He is doing in thermoelectric generator. And next, Dhiraj is doing in dye sensitized solar cell. He is synthesizing organic material, organic dye as well as a polymer electrolyte. So this guy is working tandem solar cell and perovskite solar cell. And this faculty also you might be new that is assistant director Binod Kamant. He is working in a thermoelectric generator. Of course, you might be familiar with Achna and Datta. So these are my mentors. Of course, my 12th standard teacher, I have to thank him because he only taught interestingly to the chemistry subject. That's why I can continue my undergraduate, postgraduate, and degree, even PhD. Everything I did my chemistry. And Dr. N.G. Nagaranathan, he has retired, and he is my guide in NITK. He also initially has helped so much, and frequently I discuss with my friends. He is among the one. Of course, many more friends are there. Just frequently who is discussing with the subject I put. And thanks for your valuable observations and patience. Now the forum is open for the discussions. Yeah, you can ask any questions.
Yes, sir. I think there are two questions in the chat box.
Yeah.
The first one, okay, is does the commercial polymer, for example, do commercial polymers, for example, nylon 66 and bakelite, are they tested under dynamic loading and quasi-static processes for determining various moduluses?
Yeah. Yeah, they have tested because nylon 66 and other things, that material property here it won't comes in the blends. There it acts as a resins and other applications. So once if you go for the resins and other applications, you go to check the tensile strength and the strength of the materials. So that polymers, see, normally insulator, it won't going to act as electrolyte. I have chosen the polymers, which polymer it acts as a semiconductors, and it might be helpful to enhance the conductivity. Like that I have checked the polymer.
Okay. The second question I forgot to say, it's by Dhinakar, it's the same person. Do polymers have a characteristic property on high strain rate mechanical response?
Yeah, definitely. When you are going for the different temperatures, right, based on first you have to find out at what time maximum stability, TGA, you have to do that. So based on the TGA, what is the maximum stability you can achieve that? Up to that, you can find out. Once after reach that point, thereafter, if you go for any other application, breakage might comes. So that you have to check with the TGA and the gas transition temperature of the polymer.
Okay, Dinakar, I hope that answers your questions. Sir, before, okay, there's another one by GB Raghav Krishnan.
Yeah, can we use polymers to make a bulletproof vessels? First find out what type of polymers they are using for the bulletproof vessels, and how we have to fabricate. You can check, right? See, this is not only for the electrochemical power sources. If you are able to synthesis any type of polymer, any other applications, how you have to synthesis, how you can fabricate that, that you can check. Then we can do that. Nothing wrong. Normally we can go for melt casting method. So melt casting method, the reason is you need a good amount of the material. But academically we can do that. Instead of that, you can dissolve in a common solvent and you can make a, that's what, how you can do a that is bulletproof vest means how you have to fabricate that, what kind of technology it's available, that it can be feasible in our lab or not, that we have to check. It's not only for the bulletproof, even spacecraft. Just check that how we can fabricate using that materials. What kind of fabrication they are doing. That if you can came to know that, then you can discuss with us. You can see what is the other possibilities, how we can fabricate. We can do that.
Sir, before the session, we had circulated a form asking for any, in case anyone had any questions.
Yeah.
So there are a couple over there. Is there, I mean, are composite materials feasible for application in cryogenic purposes, such as cryogenic tankers, like
See,
transportation of liquid oxygen?
yeah, all the composites are used for cryogenic applications only. But here I have what I have shown that electrochemical power sources. Composites means plenty of areas will comes, right? Even if you go for the good applications, particularly cryogenic and other things. Maximum amount of the composites application they are using for cryogenic and other things only. Okay, so you can try that, nothing wrong. You can take any of the composites and see that whether that applications is feasible for do our either mechanical lab or our chemistry lab or physics lab. That you got to find out.
Uh, a similar question is okay, what are the small scale applications of advanced materials?
So small scale applications, you can fabricate batteries, and even small batteries you can fabricate in our lab itself. Even lithium ion cell you can fabricate. And if you commercialize that what I given the current density and other things, if you try to achieve, you have the good amount of the, you may get a good amount of the turnover in your company also. In fact, one of my friend designed the job and he got a good amount of the capacity in the cathode materials, and he is doing that only, that is synthesis of the lithium ion cathode material. So you can try all the things, particularly what I shown no today, all are smart applications only. You can fabricate in our lab itself.
Uh, okay, there's another question. Is there a chance of hydrogen cell research to come back, the surge of electric cars?
Yeah, see, normally to storage of the hydrogen, you have to take a proper cylinder and you have to maintain the pressure, right? That technology, it's just we are checking. Whether hydrogen is liberating or not in academically, we can find out if you reach this potential for a particular material, hydrogen is liberating. That much only we are doing. We are not doing for any hydrogen fuel cell work or any like that any car type of work we are not doing, because it is not about particularly academical oriented. Developing that type of car is so risky, it's so dangerous also. We are not doing any type of that work. But you can take any material and synthesis, and you can find out, and you can prove that you prepare synthesis of proper material, and you can prove that this particular voltage if you reach, hydrogen evolutions may take place.
Another question is how feasible and useful are natural polymers? Uh,
Yeah, natural polymers, of course, I shown whatever I shown, no, almost polyethylene glycol, chitosan, cellulose acetate propionate, cellulose acetate butyrate, everything is a natural polymer only. The You have to extract first the natural polymers from the sources, right? Molecular weight, it comes a moderate molecular weight. So the usage, and if you go for application, there will be a no problem at all. How you are using the synthetic polymer, the same way you can use it for natural polymer also. But if there is a low molecular weight, less than 8,000 and 7,000, say for example, polyethylene glycol, you may get a variety of molecular weight. From 2,000 to 45,000 you may get. If less than 1,000 means it may act as a liquid and a semi-solid. That time you can't able to go for any other application due to less molecular weight. If you get a moderate molecular weight in the natural polymer, you can do any number of applications. No problem at all.
right. So I think Dinakar has another question. Can we observe a plastic deformation in relationship between dislocation velocity and applied stress?
Yeah, this questions, of course, it can be done, but I am not sure what kind of instrument you require for that. You go to check with mechanical department whether they are doing for the when they are applying the stress, any deformations, whether is it possible to find out or not. Normally, what we are doing, we will prepare the polymer blends and composites, and we will apply the load, and from that, what is the maximum load it's retaining. From that, we can find out the tensile strength of the material we can find out. The same way it might be available, but I am not sure about it. We have to check with the mechanical department.
Okay. There's another question in the chat box. How does research on polymer blends foray into the semiconductor industry and chip manufacturing for computer systems?
Yeah, so I one slide I have put the polymer electrolytes, that is blend polymer, solid polymer electrolyte, gel polymer electrolyte, and a blend polymer electrolytes. So the chips, you need a electrode material as well as a electrolyte. So technically, I'm not good in that how you have to prepare the chips and other things, right? So technically, you have to find out how effectively you can use what I'm giving the material. Okay, I can give your electrode material whatever the requirement you needed, that I can give your electrode material, and as well as electrolyte also. How you have to fabricate that, you have to see based on your interest. You have to go for literature survey how they are fabricating, that you have to check.
So there's another question from the forums. There's a lot of research being done in the field of nanopolymers like carbon nanotubes. How feasible are these in real life applications, and what further research is possible in this field?
See, don't worry about it, the nano and other things, because normally these questions, even when I'm doing work, I used to ask my guide also. Because where there is applications for the nano material and nano conducting polymer and nanotube, it doesn't matter. Even once if it is a nano size, if it comes, if you go for any other applications, the size of the material, it won't go, it won't, it will, that means there will be a no degradations at all. The nano size will be maintained that. The idea behind that, if you take a carbon nanotube or if you synthesis a carbon nanofiber, the surface area will be very high. So surface area will be very high means the pore capture, right? Ions will come and deposit easily, and your efficiency of the material will be high. So you can use any type of nanomaterial and fabricate whatever you require. Your properties of the applications will be enhanced only. It won't go degrade at all.
Yes. I think that covers the question session. If anyone else has any questions, they can put it in the chat box. Uh, but I think that's about it. Okay. Sir, it was a very insightful presentation.
Yeah.
And I'd like to let everyone know that, sorry, I'd like to let everyone know that Sir is open to mentoring students. And if you want, you can reach out to him, or you can reach out to him through us. You can reach out to us and we'll put you through to him. So yeah, that's about it. Tian?
Yeah. Now that the session is over, I'd like to uh, extend, I would like to congratulate sir and thank our speaker, Dr. M. Selvakumar, and our moderator, Devangshi. Uh, the talk was actually very insightful, and I'm sure that a lot of us have gained a really good insight into the field and how actually modern research is being conducted in it. I'm pleased to say that today our turnout was good, and we have people outside just Manipal. We have people from MSLS. We have people outside Mahe as well. So thank you everyone for attending. Uh, and yeah, thank you, sir. It was a really great lecture.
Okay, thanks for your opportunities. In fact, you have given one good opportunity to interact with a young mind, so it might be helpful to me also. Thank you.